My name is Dr. Laura Christianson. I'm one of the newest assistant professors at the University of Illinois, assistant professor of water quality based in the Department of Crop Sciences. So my focus area is water and water quality, and so in the state of Illinois, that means I'm interested in anything and everything tile drainage. I know this morning session here is the NREC project reporting session, but being so new, I don't quite have any NREC projects quite yet, technically. And so Jean asked me to talk to you a little bit today about my interest in water, water quality, tile drainage, and so I've titled this presentation, Ag Drainage in Illinois, Past, Present, and Future. And I like to think we have a bright future for agriculture and drainage in the state. Illinois has a very long history of artificial agricultural drainage, as many of you know. And in fact, across the Midwest, we have a very long history of artificial drainage. In fact, in the United States, we have drainage projects on the books that predate the signing of the Declaration of Independence. So clearly, artificial drainage, tile drainage, is a very important part of our history. It's a very important part of our culture, and it's an important part of our agriculture because it improves crop growth and reduces risk. It improves trafficability in the spring, and all of these things reduce risk. But of course, tile drainage also changes the natural hydrology. It changes how water would naturally move through the soil, and because it does that, it serves as a conduit for nutrients like nitrogen and phosphorus to move from our fields to our streams. The speed and the extent at which nitrogen and phosphorus move from our fields to our streams in tile drainage depends on both controllable and uncontrollable factors. Controllable factors include things like the crops that we're growing, the rotations that we do, and how we manage our nutrients in our fields. And then uncontrollable factors include things like the climate, the precipitation, how much rain or snow we happen to get in any specific year, and also soil type. And so I wanted to have a better understanding of exactly how these controllable and uncontrollable factors impact nutrients and have a better understanding of simply drainage nutrient loads in general. And so to do that, I very recently completed a meta-analysis, or a very big study looking at a lot of different research projects that have been done on drainage over the past 50 years. In this meta-analysis, I read over 400 drainage studies to really try to identify impacts of different things that we do, different strategies that we take in the field, how those strategies impact nutrient loads in drainage water. So when I look back over all these 400 studies, 400 plus studies that I read, actually Illinois was very well represented, and so the results that I'm talking about a little bit today are very applicable for where we live. When I read through all these studies and I pulled out numbers from each of the studies, I could make graphs something like this. This is nitrate load in drainage water, and across the entire database, my average load or my representative load from the entire database from all these studies that I read was about 19 pounds of N per acre that we're losing in tile drainage. Now the good thing about this big database that I made was that I could actually pull out Illinois specific numbers, and so the research in Illinois actually ended up being very close to what the entire database was saying. The representative nitrate load in drainage in Illinois was also about 19 pounds of N that we're losing per acre. Another way to think about drainage nitrate loss or nitrogen loss is in terms of the percentage of nitrogen applied that occurs, that leaves our fields in tile drainage. And so across the entire database, it was able to make this metric, and roughly the mean and median there, we're losing roughly 15 to 20% of the applied nitrogen rate is lost in tile drainage. Now how does Illinois stack up? Well, the research in Illinois tended to be just a little bit higher. We're losing roughly maybe 20 to 25% of the applied rate is lost in tile drainage. Now this is a very simple metric to think about that pops up in the literature, this percent of N applied occurring as drainage N loss, but I hope all of you are well aware that this metric is an oversimplification of the nitrogen cycle. It would never mean to imply that fertilizer nitrogen is the only source of nitrate in tile drainage, because it's quite simply not. There's also some soil-derived nitrogen that ends up in our drainage water. And I would never mean to imply that nitrogen implied in this year only impacts drainage water in this year, which is kind of what this metric is getting at. But nevertheless, this is a simple metric that's simple enough for me to think about, and it does pop up in the literature. So when I was making this big database of drainage water studies, I was also able to look at phosphorus in drainage, not just nitrogen in drainage. And the representative load across this entire database, all these studies from the Midwest and Eastern Canada, my representative load was 0.09 pounds of P per acre. So you can see the numbers here are very much lower than the numbers that we had for nitrogen. How does Illinois stack up? Well, a little bit higher, but still those numbers are sounding very low, much less than 1 pound of P per acre. We could make a similar metric, this percent of P applied occurring as drainage P loss here. Do you remember what the numbers were for nitrogen a couple slides ago? We were talking about 15 to 20 to 25% of the nitrogen rate being lost through our drainage pipes. Here, look at that x-axis, 0 to 1%. So that's very small in terms of economics. Losing 15, 20, 25% of something that you've paid for, that definitely gets me awake. Losing 1%, I might be a little less concerned. The trick with phosphorus, though, compared to nitrogen in terms of water quality, is that it's these very small numbers, this less than 1% that we're losing, that causes situations like this. I hope some of you remember about a year and a half ago, summer of 2014, in Lake Erie, there was a massive algae bloom that shut down the drinking water source for the city of Toledo, Ohio. So neighbors, just to our east, 500,000 residents had their drinking water supply shut down because of this algae bloom, which was caused by phosphorus. And so being new here at the university, I feel very strongly that it's our responsibility to have solutions ready for the agricultural community to avoid situations like this. These are the situations that get people to call their legislators. These are the situations that are driving policy. And so these are the situations that we want to be out in front of. So we've talked a little bit about the past, this big meta-analysis that I did looking backwards. Now we'll talk a little bit about the present. I know all of you in this room, I know for a fact that you have all heard of the Illinois Nutrient Loss Reduction Strategy because Kristen just mentioned it within the past 30 minutes, so I know you've all heard of it. Other states in the Midwest have been tasked with coming up with their own strategies to help develop solutions to reduce negative water quality impacts that end up in things like the Gulf of Mexico hypoxic zone, which Kristen mentioned, also that Lake of Erie situation. So I wanted to look at these three practices from Illinois, or strategies from Illinois, Iowa, and Minnesota, all heavily tile drain staged. We're all dealing with some of the same issues with nitrogen and phosphorus and drainage water. So I wanted to create a table to compare the different strategies, the different practices that are in the three strategies that I mentioned here. You can see we have infield nitrogen management practices, those first columns there, reducing nitrogen rate, shifting timing, use of N inhibitor. All three of these strategies included infield cropping management practices like cover crops, like perennial energy crops, or an extended rotation that includes a perennial. And then we all have edge of field or more structural type water quality improvement practices, things like Woodchip Bioreactors, things like constructed wetlands. Now, one of the most important things to note about this chart is that each of these practices has a different nitrogen rate reduction effectiveness. So every practice is different in terms of how much it'll clean up water quality. All of these practices are also different in terms of cost, and not just in terms of overall cost, but when the cost will occur for your practice. For example, a constructed wetland is a big expense, right? Big capital expense right up there on day one to do the construction. But then you're pretty much done with most of the expense compared to a cover crop. That's something that you want to do every year. So that's an ongoing annual cost. Practices differ in effectiveness, they differ in cost, and then they also, of course, differ in suitability. So one might be very interested in a cover crop, but maybe not so interested in a nitrification inhibitor. Someone might be very interested in an inhibitor and some of the infield practices, but maybe not interested in a structural practice. So as you know, every farm is different, different practices will work in different locations. And finding where that one or group of practices will work, that's where we are with the research. So maybe through some of the practices very quickly. 4 R's, improved nitrogen management, reducing the rate to the MRTN level as Emerson was talking about. Another 4 R's practice, talking about shifting nitrogen application from the fall to the spring or doing some split applications. I think you'll hear more about 4 R's practices this afternoon. We also have cover crops, which are one of the more popular infield practices here in the Midwest. There's a lot of research momentum behind cover crops, a lot of demonstration momentum behind cover crops, and in the Illinois strategy, reduces loss by 30%. Including a perennial in your rotation, doing an extended rotation, or growing a perennial energy crop, that's one of the most effective things we can do. Reduces nitrogen losses and drainage by 90%. That's one of the highest scores that's out there. Of course, not everyone's going to be interested in growing alfalfa or growing an energy crop like switchgrass. But again, it has one of the highest scores. There's obviously some economic impacts here. If everyone were growing alfalfa, the price would fall through the floor. So it's a complicated, every strategy is complicated. Wetlands are one of the best constructed or structural practices we have. Do I have any hunters here? I see a couple hands. Wetlands are great for water quality improvement, reducing nitrogen and phosphorus in drainage water. They also provide a lot of really great wildlife benefits and additional benefits like flood retention. And that could be something important considering some of the rains we've just had. Reduces in-losses by 40%. And then woodchip bioreactors, that's a practice near and dear to my heart because I've been doing research on these since 2008. Woodchip bioreactor is really just a trench filled with wood chips that you run your tile drainage through. And there's good microbes, these denitrifying microbes that use the carbon in the wood chips as their food source. And as nitrate flows by them, these little microbes convert the nitrate to nitrogen gas. Like a very simple water treatment plant. Reduces in-loss by 1/4. So we've talked a little bit about the past, we've talked about present options, and in my role at the university, one of the most exciting things that I'm thinking about is what's cutting edge for drainage research. What are we on the cusp of to take us to the next level in terms of having good drainage systems that do what we want them to do, but also help clean up water. Hopefully some of my research won't be as painful as these guys. They're paying the price. So we talked about woodchip bioreactors just a second ago, and this is how a woodchip bioreactor would normally look on a tile drain. And I was working with a farmer in Maryland recently, and he said, well, I don't have room on my tile drain for a woodchip bioreactor, but I want to do something like that. And so I went back to the drawing board and said, well, hey, let's just put these wood chips in your drainage ditch. And so we excavated the bottom of the drainage ditch. We laid a layer of wood chips down. We put gravel on top of the wood chips so they wouldn't float away. And so this picture was actually taken a month ago. We installed this woodchip bioreactor in his drainage ditch. So he still has the drainage capacity of that ditch to move water downstream to get it off his fields, but he's also providing some water quality benefit. I'll also point out with this picture here, that green you see is his cover crop. So this was a guy that was already doing some good stuff, and he was looking to the next thing. What's the next thing that I can do to help produce crops and also clean up water? Another practice that I like that we're really on the cusp of is called a saturated buffer. Maybe some of you have heard of the practice of a riparian buffer or a stream buffer, which is shown here in the picture. The stream buffer goes between your field and the stream, and those buffers provide a lot of good benefits like wildlife habitat. They help stabilize the soil of the stream bank so you don't have the stream bank sloughing off into your stream. It also can help cool the water, which is good for fish if you have trees in your stream buffer. But the challenge with a buffer is that if you have a tile drain, that tile drain usually goes straight through your stream buffer. So that stream buffer is providing a lot of good benefits, but the tile drain short circuits it. So with a saturated buffer, we have a twist on this buffer technology by installing a control structure that holds back drainage and sends it out into little side manifold arms or perforated arms, so that that drainage water doesn't go straight through the buffer. It actually goes out to the side and moves through the soil of the buffer. And when that drainage water is moving through the soil of the buffer, you get a good benefit of natural microbes that are living in the soil. They clean up the nitrate. There's plants that can take up the drainage water then, because it's not just short-circuiting straight to the stream. Now, this is also one of my favorite practices that we're just on the cusp of in terms of tile drainage. Have any of you ever had the thought, maybe in late July or August when it's really dry, boy, I wish I could have saved some of that drainage water that we sent down the creek in March, April. The crop could really use it now. Well, with this practice, recycling drainage water, the idea is you save that drainage water, that's your water, that has your nitrogen in it. You save that, hold it back, and then recycle it to the crop when you need it later in the summer. So obviously this is not an inexpensive practice to do, because you need a pond or a reservoir, or at least room to install or construct a pond or reservoir. But then when you think about the potential yield benefits of holding back your water in a dry year and using it for the crop when you need it, there's significant yield potential benefits, especially in a dry year. And from a water quality standpoint, which is my real interest, this is a potential for a zero discharge system. So you're keeping your water, you're keeping your nitrate, it's not going downstream. So that's all I had today. But if you're interested in any of the things I've talked about, and I hope you are, feel free to contact me, and we'll see if we have some common ground.